education. I am not a computer scientist, but I work in an area which is probably very close to one of the areas which is very close to what computer scientists do. So I'm a statistician, and it so happens being an Indian Statistical Institute, which has a large group of computer scientists, I often interact with them. And as I was preparing this talk, I was thinking about one of my colleagues who passed away 2 years ago. It was a CMS. It was he who got me into all this business of pattern recognition, classification, clustering, image processing, and most of the things that I have done, he had some influence in some way or another. What I'm going to present today is based on some of the joint work that I have done with two of my former PhD students. One of them is now a faculty at IIT Shivji. Other one is a colleague of mine, Mohani. After doing his PhD, spent some time in IIT Kanpur and all these. And in all these works, I think when he was alive at that time, we used to consult him from time to time. And so, in many ways, what I'm presenting today, there is some influence in some form or other. So, and I requested Shubhaji and Anil to be present here because I think I have stopped working on classification for about 7-8 years ago now. In fact, after Murthy passed away, I don't think I have touched that topic now. Okay, so it's like I lost one of my best collaborators. And, so, in some sense, also I was moving away from that area. So, and he passed away. So, in some sense, when I was preparing this talk, it was kind of a recollection of my interaction with Murthy on various occasions. So, anyway, let me start without further discussion on other things. So I was told to give a talk on foundations of machine learning, and I was also specifically told that I should speak a bit on Fisher's work, C.R. Rao's work, Mahalanobis' work. So I have tried to prepare the talk accordingly. And in some sense, when people ask you to give a talk on such specific topics, it becomes a little easier to prepare that. So it was not so difficult to prepare. So I kept on procrastinating, and then I was doing it at the last moment, and then maybe you'll find a few typos in my slides. So let me move to the first slide. So we will start with a brief history of classification. So it started with this classic paper by Fisher that appeared in 1936. The title of the paper was The Use of Multiple Measurements in Taxonomy. So Fisher was actually interested in the taxonomic classification of different species of irish. He had measurements on the lengths and the widths of the sepals and the petals of the flowers of 3 different species, namely Iris setosa, Iris virginica, and Iris versica. If you are familiar with these flowers, they are very different in their look, but Fisher wanted a mathematical or say statistical. Fisher was not thinking about the word statistics at the time, I'm sure about that. So he wanted some sort of a quantitative tool where based on certain measurements on these flowers, you can classify them as either setosa or virginica or versica. So that was his idea. And so Fisher was a geneticist, and he had interest in biology in general. So when he developed these tools, the problem was essentially originating from taxonomy. Now, what this has to do with Mahalanobis distance? Okay, so you note that this Fisher's paper appeared in 1936 in the Annals of Eugenics. At that time, Fisher was the editor of Annals of Eugenics, and it's a fairly long paper. I mean, if you count the number of pages, it's only 10 pages, but in Annals of Eugenics, if you look at those old issues, they're very long pages and short, fonts are very small, and so it's a fairly long paper with a lot of interesting discussion. Now, Mahalanobis's work on Mahalanobis, what we call the Mahalanobis distance, it started in 1920. But this is a paper that I'm referring to because it appeared at the same time as Fisher's paper on classification. And this is actually his special lecture in the Proceedings of the National Academy of Science. This National Academy of Science is actually the predecessor of Indian National Science Academy in Delhi. After I became a fellow of Indian National Science Academy at Delhi, I was reading the history, and I found out that at that time, this proceedings was published from this National Academy of Science, which it was used to be called at that time, and it was located in Calcutta. It got shifted to Delhi later. So it is the proceedings of the predecessor of Indian National Science Academy where this paper appeared, and it is called the Generalized Distance in Statistics. But as I said, the origin of this paper goes back to Mahalanobis' interaction with Nelson Annandale. Nelson Annandale was at that time Director General of Geological Survey of India, and he was also the Director of Indian Museum. He was an anthropologist dealing with a lot of anthropological, rather anthropometric data, and he wanted somebody who can analyze the data for him. So Mahalanobis met him at the Nagpur session of the Indian Science Congress, and those two people found some common interest, and they started working on this data that Annandale collected on the Anglo-Indian populations in Calcutta. This eventually led to the development of this famous Mahalanobis distance. Now, let me tell you what Mahalanobis distance is. I'm sure many people in the audience knows that, but since I'm doing a brief historical review, I thought it would matter if I just put down one slide on that. So this is Mahalanobis distance. You look at the difference of a point from the mean of the distribution, and then you standardize by the dispersion, and that's Mahalanobis distance. And I have the habit of using multiple notation for Mahalanobis distance. So maybe on some later slides, instead of this square, you'll find I'm writing MD there. MD stands for Mahalanobis. It's the same thing. Sometimes I write this square, sometimes I write MD, they mean the same thing. Okay? So if you have this sigma matrix and identity matrix, it's really the Euclidean distance, the standard Euclidean distance that we are all familiar with in geometry. Okay? And when you have this dispersion matrix there, it's a way of standardizing the variables using the dispersion of different variables, which makes it free from the unit of measurement. So this distance is something that is free from the unit of measurement. That's why it is very important in statistical analysis. If you take the Euclidean distance, sometimes, for example, if you have anthropometric data, you might have data on the heights of people, then the various measurements related to their skull. And so, I mean, it will be difficult to combine them using Euclidean distance. You need to do some standardization before you combine these variables. And that standardization was done by Mahalanobis through this dispersion matrix. Now, coming back to Fisher's linear discriminant function, the Fisher's linear discriminant function is defined like this. If you look at Mahalanobis distance and Fisher's linear discriminant function, immediately you don't see any obvious connection, except that both involve these mu's and sigmas. So if you have two populations with means mu1 and mu2 and a common dispersion sigma, this is how the Fisher's linear discriminant function is defined. And you see it is a linear function in X. These mu's are related to the population, and this is the linear function. So what is the connection between the two? In fact, neither Fisher nor Mahalanobis ever actually realized on their own that these two things are so deeply connected. The connection was made much later by a very famous statistician, and I'll come to that later. So let me tell you how Fisher was developing his linear discriminant. So here is the connection. As I said, there is a connection, and if I tell you very briefly what is the connection is Fisher's linear discriminant function corresponds to the separating hyperplane that separates the points which are closer in Mahalanobis distance to one population from the points which are closer to the other population. Let me go to the next slide and show you a picture. So this is like this. So suppose these are points that represents measurements from one population, these blue points. So if I put an x-axis here and the y-axis here, this could be the heights and weights of something. Okay, and these are the points representing the heights and weights. Okay, and here again we have the heights and weights from some other population. Okay, now if I look at the red dot here, this red dot, if I calculate the Mahalanobis distance of this red dot from this green population, of course that's going to be much larger than this Mahalanobis distance from this blue population. You can calculate it the way I have given you the formula. Similarly, this one, this red dot is closer to the green population. Now, if you look at Fisher's linear discriminant function, that is really this line. Okay, so you see the ones that are closer to the green population, they lie on one side. Those which are closer to the blue population, they lie on the other side. That is the connection. But as I said, neither Fisher nor Mahalanobis ever realized that at the beginning. Then how did Fisher got it? Well, Fisher's choice of his linear discriminant function was motivated by the fact that this linear function maximizes what is called Fisher's two-sample t statistic computed from linear functions. Fisher was actually involved in a lot of agricultural studies. In fact, before joining the University College at London, Fisher was working at the Rothamsted agricultural station. Okay? In fact, there is something very interesting between Fisher and Mahalanobis. These two people were great friends. Okay? And there are many factors which made them great friends. One of the factors was that they were both, in some sense, these two people both strongly disliked Carl Pearson, who was at that time editor of Biometrica and was also involved in similar research. In fact, Fisher took this job in Rothamsted, declining an offer from University College London because the offer was made by Carl Pearson. But when Carl Pearson passed away, Carl Pearson was the Galton professor, and Fisher took the Galton professorship and came to University College London afterwards. So anyway, so Fisher was deeply involved in agricultural studies, and in the course of his agricultural research, he developed a lot of statistical tests, and one of them was this Fisher's two-sample t-test, which is actually a way of comparing the means of two different groups. And Fisher realized that if you have several measurements coming from two different groups, you take a linear function to reduce all those measurements into a single linear variable, a single real variable, and you calculate the t-statistic based on that. That t-statistic, then you try to maximize with respect to the choice of your linear function, you end up getting the linear discriminant function. So if I move one step backward, so this linear function that I have here, it is the linear function that maximizes Fisher's t-statistic. So in some sense, this is the linear function that gives maximum separation between two populations when we restrict the separation to linear functions of the data. So that was Fisher's motivation, because Fisher was developing this t-test, f-test, and all these things. So that was Fisher's motivation. Now comes the question that, okay, all this is very nice. So suppose that you know all these connections. Okay, so this looks very nice that Fisher's linear discriminant function actually separates the points according to that rule that whoever is closer to one population according to Mahalanobis distance, it falls on one side of the line. In higher dimension, instead of line, is going to be a hyperplane. And the points that are closer to the other population, it falls on the other side of the line of the hyperplane. And it also maximizes Fisher's distance. But after all, you are interested in making a classification. So your objective is to get a classifier that gives you lowest misclassification. And what is the misclassification rate? It's like, suppose I have Fisher's problem. So I want to classify these Irish flowers into different groups. Okay, so if I classify an observation to setosa, and if it is not really coming from Iris setosa, it's coming from Iris versicolor, then I make an error. So in what percentage of cases I make an error and in what percentage of cases I make the right classification. That should be the ultimate criteria to judge a classifier. And that is what we call the misclassification rate of a classifier. So neither Fisher nor Mahalanobis was thinking along that direction. They had no way of getting their hands on the misclassification. They were looking at things in a more geometric manner. Okay, so geometrically, this point is closer to that population or this population, or geometrically it is on one side of the hyperplane or other side of the hyperplane, or geometrically maximizes a T statistic. But nobody was looking at the misclassification. So who did the misclassification? So I will come to my next slide. So it is C.R. Rao, who is another big name in statistics from India. So it was C.R. Rao when he was in UK doing his work in Cambridge. At that time, Fisher was in Cambridge, and C.R. Rao was actually having a position in Indian Statistical Institute, but somebody wrote a cable to Mahalanobis asking for 2 statisticians to go there to work on anthropological data that they have at the museum, Cambridge Anthropological Museum. And C.R. Rao was deputed there, and C.R. Rao took this opportunity to do his PhD research under the supervision of Fisher. Now, a lot of people don't know something interesting about C.R. Rao here. It's like computer scientists or electrical engineers probably know C.R. Rao's name more in the context of his work on information boundaries, what is popularly known as Kramer-Rao. Now, both Rao-Blackwell theorem, for which he is going to be ever famous in statistics, which is something that all undergraduate inference courses will cover always, and Kramer-Rao lower bound, they were both invented in 1943-44. When C.R. Rao didn't have a PhD degree, he just completed his master's in 1943 and joined Indian Statistical Institute, and he was teaching in some training program. And as he was teaching, out of some questions that he had from the students, he invented these 2 famous results. And it's kind of amusing that after inventing Rao-Blackwell theorem and Kramer-Rao lower bound, one still takes a PhD degree. And he went to Fisher to get his PhD degree. I requested him to supervise him. And C.R. Rao's request was gladly accepted by Fisher. And Fisher said that, okay, I mean, you work on your own, I'll try to help you as much as I can. So you see, this is the paper that C.R. Rao published out of his PhD thesis. And this paper is a long paper in Journal of the Royal Statistical Society, and it's a discussion paper. There are a lot of discussions that they're discussing in this paper. It is essentially C.R. Rao's PhD thesis. And you see the remarkable similarity between the names of this paper and the name of Fisher's original paper. Here, the name is the utilization of multiple measurements in problems of biological classification, whereas Fisher's paper had the title, The Use of Multiple Measurements in Taxonomy. The difference between the problems that these 2 people considered, where Fisher was interested in taxonomic problems, whereas C.R. Rao was considering problem in archaeology. So as I said, C.R. Rao was deputed from Indian Statistical Institute to work in the Cambridge Museum. And in the museum, they had a lot of data coming from archaeological excavation. And they were trying to classify the skulls into Iron Age and Bronze Age. And that's where C.R. Rao was involved. And his PhD work with Fisher had a close connection with that. And while doing this, he developed all these results on misclassification rates, which gives the real justification to Fisher's linear discriminant function as a proper or adequate classifier. So let me give you a summary of the main results from C.R. Rao's paper. So this is one of the key results. The linear discriminant function has Bayes risk optimality for Gaussian class distributions, which differ in their locations but have the same dispersion. Okay, so Bayes risk optimality essentially means optimality in terms of misclassification. So if you have any other classifier, you compare its misclassification rate with the misclassification rate of Fisher's linear distribution function. If the population distributions happen to be Gaussian satisfying this condition, then the overall misclassification rate for the linear classifier of Fisher is always going to be at least as good as any other classifier. Okay, so if you make comparison with any other classifier, it's not going to be able to beat Fisher's linear distribution function. That's the difference. In fact, this result remains valid if you deviate from Gaussian distribution and move to more general elliptic distributions. Okay, so Gaussian distribution is a special case in this entire family of elliptical symmetric unimodal distributions. Okay, now in all these problems, just to make sure that you don't miss some subtle technical points, we are considering a balanced case, namely that it's like when you have the training data, they are balanced, reasonably balanced, so that you don't take priors to be very different. If the priors are different, then some adjustments are needed, but still the linear discriminant function remains valid for Gaussian distribution. For elliptic distribution, it will not be valid if you have an unbalanced case. There you need some adjustment. So that is about the history. Okay. Now let's get to some interesting examples. So here is some example. I describe it algebraically first, and then I give you some pictures. Okay. So first example, you have a mixture of two Gaussian distributions, and then the second population is also another Gaussian distribution, and then the second example is a mixture of uniform distribution in the d-dimensional space. The second population is also a mixture. The important thing is here, all these classes have the same location, but different scatters. So they don't differ in location. So as such, if you calculate the Mahalanobis distance, ignoring the issue of scatter, there is difference in scatter here, and the Mahalanobis distance that I have given you, that is defined for equal scatter. But ignoring the scatter, if you just look at the difference in means, that is 0. So as such, Mahalanobis distance or Fisher's linear discriminating function will not work. But what is the Bayes classifier? In fact, when Sierra worked out the result, Sierra actually showed that for any distribution, the Bayes classifier is actually given by the likelihood ratio. So it's like if you have two classes and you have their class densities or class distributions, it is the ratio of the class densities that gives you the optimal Bayes classifier. And that is called the likelihood ratio. Okay. So if I draw the Bayes class boundaries for these two examples, it will be like this. So you see, these gray areas are the areas for point to be classified into one population, and the dark areas are the areas where it is to be classified into other population. Now, for the second example, it's actually if you are able to identify these Bayes class boundaries, your classification will be perfect, because if you go back, it is a uniform distribution. So it is supported on some specific sets. And so it's like outside that set, you don't have an observation if it is coming from that particular distribution. Okay. So here, if you are able to identify the Bayes class boundaries, your misclassification rate will be 0 in the same. The Bayes classifier will be a perfect classifier. In future, I'll refer to such problems as in some sense degenerate, because it's in some sense quote unquote trivial or degenerate. But that's not the case here. It's not a degenerate or a trivial problem, but these are the class boundaries for the Bayes classifier. And you see they are these concentric ellipses. Those are the class boundaries. So if I have a line or a hyperplane or even a quadratic classifier, which will be like a parabola, or in the other higher dimensions, some parabolic surfaces, paraboloidal surfaces, they are not going to capture the Bayes class. So here, the class distributions involve elliptical symmetric distributions. I have already said that. I've also said that they have same location and they differ only in their scatters as well as shapes. And no linear or quadratic classifier will work here, as they will fail to capture the Bayes class. So The question is, does it mean that for such problems, Mahalanobis distance or Fisher's linear classifier completely collapse? Let's try to understand it more. But before that, let's look at the performance of different classifiers. So here is the performance of different classifiers. Okay. So as I said, for the second example, if you look at the Bayes classifier, see its misclassification rate is 0. So it's coinciding with the horizontal axis. And then I have taken a bunch of very standard simple classifiers that anybody in machine learning or working in pattern recognition will be familiar with. So this K nearest neighbor, kernel discriminant, kernel, by that mean I kernel density estimate, okay? Not the kernel in support vector machine. Okay. Then I have the linear discriminant classifier and the quadratic discriminant classifier, and then the Bayes classifier, and you see the performance of them. So as the dimension, I plot the dimension in logarithmic scale because I have allowed the dimension to grow very fast. So it's like first I take a dimension, then I go to 5, 10, 20, 50, and 100. So it is increasing exponentially. So I plot the dimension in logarithmic scale, and you see the misclassification rate is falling for the Bayes classifier here, and here the Bayes classifier is always perfect. Whereas for all other classifiers, it's pretty bad. In fact, you have these classifiers that have 50% misclassification. 50% misclassification means that you are not doing any intelligent analysis. You are just tossing a coin. It's like you have a weather forecaster who is tossing a coin, and if it is head, then forecast that it is going to rain today. Otherwise, if it's tail, the forecaster will say that it is not going to rain. That classifier will have 50% misclassification. Okay, so you don't need such a classifier. So clearly, linear discriminant analysis and quadratic discriminant analysis will fail. And it is not just linear discriminant analysis or quadratic discriminant analysis. There are other classifiers which will also fail. Okay. So now let's try to do a little bit of, at this point, for a while, maybe for 5-10 minutes, it's going to be slightly mathematical and technical. But for computer scientists working on pattern recognition and machine learning, this should not be overly technical. Okay. So suppose we have some class densities that are elliptic. And again, you see that I told you that sometimes I use this square and sometimes I use Mahalanobis distance. So this entire expression for elliptic distribution, it can be written as a function of the Mahalanobis distance. So if you calculate the class posterior probabilities, the class posterior probabilities turn out to be something like this, where this pi is at the primes. So if you have confusion, forget about these pi's, treat them to be a balanced case and take these pi's to be all equal to half, then you can drop this pi's completely. And P2x, the class posterior probability for the other class is this. And then if you do a little bit of algebra, it turns out to be something like this expression. Okay. Now, it's a very well-known model. It's called the logistic regression model. And if here, instead of any general elliptic distribution, you happen to have Gaussian distribution, then something interesting happens. That is, so these are the expressions for the class posterior probabilities. I have written them in a different way. And so this is what happens when you have Gaussian distribution. If you have two normal populations, then we get what is called the linear logistic regression model, which actually leads to something like Fisher's linear distribution function. When you have two normal populations which differ in their scatter also, not just in their means, we get the quadratic logistic regression model for the posterior. And this is related to the quadratic. Let me go back and let's look at these expressions for posterior probability. So ideally, the Bayes classifier tries to classify an observation into the class for which the posterior probability is larger. So you have two class posterior probabilities. One is this one and the other one is this one. You will calculate this for an observation X. And if the observation X gives you a larger value for this one, you classify that into class 1. And if it gives you a larger value for this one, then you classify it into the second class. That's how it goes. Okay. And this is what is the main or key observation here, that this posterior probability satisfies what we now call a generalized additive model, which goes back to a famous paper by Hesty and Ticcioni in 1990. These two people are very well-known names in the machine learning and pattern recognition community. And this is one of their early work, which is related to their PhD thesis, which they did when they were in Stanford. So the interesting thing is that, so you see, I'm writing these things in terms of a new variable z, and this z is nothing but this Mahalanobis distance of the observation from one population and the Mahalanobis distance from the other population. So essentially what is happening is, this is what is happening. So we replace the original feature variables by the Mahalanobis distance from different classes. So we map the original features into the Mahalanobis distance. And then if I go back, this is what happens. This looks very complicated, but this is just an extension of what you have seen in my earlier slide when we had only two populations. Okay, so maybe I go back to the two populations. Okay, so this is the thing. So you essentially need to fit a generalized additive model to the data after you replace the original feature variables by the Mahalanobis. That is what is said here. And then you use the backfitting algorithm to estimate the posterior probabilities from the training. So that's the new classifier, and that will give you, that will eventually capture the base class boundaries if you have sufficient amount of data. So you can prove the posterior consistency and all other results for this classifier. So you see, linear classifiers or quadratic classifiers will not, but Mahalanobis distance still is one. All that you are doing here is changing your feature space. The original feature variables get mapped into Mahalanobis distances, and then it is some form of a non-parametric logistic classifier. Okay, now let's move on further. Okay, this much we have, if we have Gaussian or elliptic distributions or various combinations. We can have non-elliptic distributions, we can have multimodal class distributions. Will Mahalanobis distance work there? Well, possibly not. If things are very bad and very irregularly behaved, Mahalanobis distance is not expected to work very well there. But it will work for a very large class of populations, namely what I have written in there. If you have mixture models of class distributions, which are mixtures of elliptic distributions, you can really use the same additive logistic regression approach. Let me show you. So forget about this slide for the time being. So in the training data, we have class levels, but subclass levels are not available. What are subclass? So, okay. So we have mixture model. So each population is a mixture. And that means each population consists of several subpopulations. Now, in the training data, you have the levels for the classes. You don't have the levels for the subclasses. So this problem is like the earlier problem with a missing data issue. So in the training data, we have the class levels, but not the subclasses. If you had known the subclass levels, then you could once again use the backfitting algorithm to estimate the subclass question. And subclass levels can be treated as missing observations, and then you can use the famous EM algorithm, which was invented by statisticians long ago and widely used in machine learning. Okay. Now let me go back to that slide with all those complex expressions. So you see, because of that mixture, you now have this, for each density, you now have a sum, and for the entire class posterior, it is of this form, and the posterior probability for the subclass satisfies the multinomial additive logistic regression model. But the difficulty is that I cannot really calculate the subclass posterior probabilities because the subclass levels are not available, and that's why I appeal to EM algorithm. The EM algorithm enables me to handle this missing data issue. How does it do that? Here comes the final algorithm. So there is an initial E step. Okay. So this E stands for estimation. What are you estimating? You are estimating the missing class subclass levels. So the subclass levels are estimated by appropriate cluster analysis of the training data in each. So you do some cluster analysis. There are a whole bunch of clustering algorithms available. Use anyone that is your favorite. It's only an initial thing. Any reasonable cluster analysis algorithm will work there. Take anything that you like, and that will enable you to get some initial clustering of each population, and that you can track as an initial approximation of the subpopulation. And then comes the next step, which is called the M step. M step comes from maximization in the maximum likelihood. Once the subclass levels are obtained, subclass posteriors can be estimated by fitting a non-parametric multinomial additive logistic regression model using the backfitting. This backfitting algorithm is really an approximate maximum likelihood estimation. That is why I use this term M. It is a very classic algorithm, EM algorithm, and that E stands for estimation and M stands for maximization. Because this backfitting algorithm is essentially a maximization algorithm, I use the letter M here. Okay. Then in subsequent M steps, so once you do the backfitting and then you classify things into different subpopulation, then the subclass levels are again estimated by the subclass posterior. And an observation is classified into the class having the largest posterior. You can do the same thing for the subclasses. So then you iterate. So this is the final one. So you see, even for a very complex class of distributions, namely mixtures of elliptic distributions, which includes mixtures of Gaussian distribution and the special case. In fact, there is a huge literature on pattern recognition and machine learning where they use this mixtures of Gaussian distribution as the fundamental model. This is more general than that, mixtures of elliptic distribution. Okay, and that can be handled by Mahalanobis systems via this backfitting algorithm and generalization. Now I will move to the next level. This is not, you will not see the connection immediately with Mahalanobis distance. I will make the connection a little later. But let me go back to that slide that I had shown you long ago. Okay. So this was the fundamental idea that Fisher had. Okay. So you have these blue dots and the green dots, and the red dot is classified into the blue because it is here, and this red dot is classified into the green population because it is here. Now, Fisher was deciding that based on linear discriminant function, and if you connect it with the Mahalanobis distance, then you can decide it in terms of Mahalanobis distance. Okay, but you can decide it in another way also. Okay, so visually, this dot is located well inside this cloud of blue dots, whereas this one is located well inside this cloud of green dots. So it probably belongs more into this green population, whereas this one belongs more into this blue population. Now I go to what I wanted to show you next. Okay, so suppose I have this cloud points. So this is what I call a data cloud. Okay, so set up. Now I draw the picture in dimension 2 because it is easy to draw it there, but it can be in any dimension. In third dimension also you can try to visualize it. Beyond that it will be impossible. Okay, so you have this point, and you think that this point is well within this cloud, whereas this point is on the boundary, this point is on the boundary, and so on. So what they are sort of not so much in that center, but in the boundary. So this is in some senses deep inside, whereas this one is not so deep inside. So this motivated people in the 90s, 1990 and around that time when I was a fresh PhD student, completing, I was not, I shouldn't say fresh, I should say I was a fresh graduate, the PhD degree. This used to be a very fashionable area of research at that time. Data. What is data depth? This is an idea that was popular not only with statisticians at that time, and still popular with a group of computer scientists who are interested in computational geometry. So, what is data depth? Data depth of a point measures the relative position of that point in a given data. It gives a center outward ordering of the points relative to the data. Now, how do you measure the depth of a point? So I now need a quantitative measure. Intuitively or visually, it's clear. If I give you a picture, you'll say that, okay, the blue dot is very much inside the cloud, whereas those red dots are outside. So one approach that goes back to this famous statistician John Tukey is based on lines or hyperplanes, which divides the entire space into half spaces. Let me show you another picture. This is called Tukey depth or half space. So you see, if you look at this blue point and I draw a line to that point, I can draw many lines, then in some sense, all those lines will give you an equal split of the data points on both sides. Whereas if I draw a line to this red point, as I have drawn here, you can always draw a line in such a way that most of the points are only on one side of the okay. This is not possible here. No matter how you rotate your line, it's always going to give you more or less equal split. So if the point is deep inside the cloud, that's what happens. Whereas if a point is on the boundary, then you'll be always able to find some line, or in higher dimensional space, some hyperplanes where most of the points are on one side. So depth is measured like this. Okay, so we take the minimum of the proportion of data points in any half space of the line to a point after considering all possible lines. So for the red point, you can get the depth to be small. In fact, you can find one line where all the points are on one side, so the minimum of the two proportions is going to be 0. Whereas here it's nearly equal, so it's always going to be nearly half. So now you can take a different way of classifying observation. Okay, so you can classify an observation into a population for which the depth is larger. Okay, but before that, let me show you another version of depth, which is in some sense computationally easier in higher dimension. Because in higher dimension, if you calculate all these hyperplanes and check whether the points are on one side or the other side, is a huge amount of computation, even for moderately large dimension if your sample size is large. Okay. So this is something that is much simpler, and that came much later. Okay, so you see that I take this green point and I draw these lines joining this green point with other data. So I'll get different arrows. I have drawn only a few, but I can do it for all the. Okay, and then what happens is that so these different directions, they will cancel out each other if I look at that resultant vector. Okay, and so the norm of the resultant vector is going to be nearly 0. Whereas if I look at this red point, because it is outside the cloud, all these points that are joined with this line, they will form an arrow or a direction which are pointing in one direction. So when I average them, I'll get a value. If it really moves farther away from the cloud, I'll get an arrow that has length nearly close to 1 if I take unit vectors as the arrows. Okay, so this is another way of defining whether a point is central or peripheral or on the boundary. So classification by data depth will be like this. Now I bring back that slide again. Okay, so forget about this line. When I'm asked to classify this point, I'll calculate its depth with respect to the blue population. I'll calculate its depth with respect to the green population. And then I'll classify it into the class for which the depth is larger. Of course, the depth is going to be larger for the blue population. Whereas for this point, the depth is going to be larger for the green population. So that is depth-based classification. In the 90s, it became very popular, and there are a lot of research that went into that. It is still a very popular topic of research in statistics literature, but I guess the computer scientists have not become overly enthusiastic about it. Now, I think it has a lot of potentials. One advantage is that it does not involve computation of the dispersion matrices and such things. So if you really have a distribution which is very skewed, or if it is very heavy-tailed, then these depth-based methods might have better performance, and it might have better performance in other situations also. Okay. So, but the interesting thing is, if you have an elliptically symmetric and strongly unimodal distribution, then the depth of a point relative to that distribution. So I have defined depth for a data cloud. You can define depth for a distribution also in the same way. Okay, so you can think of that cloud as like an empirical distribution coming from a population distribution. So you can define a theoretical depth for a probability distribution also in an identical way. Anyway, I don't need to go into those technicalities. If you are interested in knowing data type, there is a huge literature on that, and you can just read that. But the most interesting thing for our talk today is this fact that for any elliptically symmetric and strongly unimodal distribution, the depth of a point relative to that distribution is a decreasing function of the Mahalanobis. So, for such distributions that are elliptic and strongly unimodal, if you are classifying using data depth, your classifier is actually equivalent to classifier Western Mahalanobis. That's a beautiful fact. So Mahalanobis distance is hidden everywhere. Whether you do classification using data depth or you do classification by additive logistic regression, it's there. Now, that is true, of course, if you have elliptically symmetric or some, in the earlier case, you can allow mixtures of elliptic distribution also. Now, I think this is what I intended to tell you about what happens in finite dimension. Okay, so I have given you a title, which I have stolen from that from the title of that famous book by the physicist George Gamow. Okay, and there I deliberately put that word infinity because here infinity is a specific object. It's not something which is sort of beyond the horizon or something like that. The infinity is there. So for the last few minutes of my lecture, I am going to talk about what happens if you are in infinite dimensional spaces. Now, why infinite dimensional spaces? Let me give you a little bit of history now. Okay, so I have not prepared any slide for that, but I can only tell you a little bit of history of that. Again, it goes back to C.R. Rao. So after completing his PhD in 1948, C.R. Rao returned to India, and he was working in Indian Statistical Institute. And one of the major activities of research in Indian Statistical Institute in those days, when C.R. Rao was working there and Mahalanobis was also quite active in the 50s, was analysis of anthropometry. And this anthropometric data used to come with a very, very large number of information. So it's like there may be a few samples, but on each sample, they will take a very large number of observations, which in today's language we call high dimension and low sample size problem. So C.R. Rao was working on that in the 50s. Anyway, okay. So while working on this problem, C.R. Rao was thinking about how to handle these problems mathematically. And C.R. Rao realized the best way to handle these problems mathematically is to embed this high dimensional problem into an infinite dimensional probability space. So you take an infinite dimensional space and you consider probability measures on that infinite dimensional space and you embed your data there. This embedding is a very classic tool used in mathematics, and C.R. Rao just adopted the tool for this classification. And his major work, which is in my opinion a classic in the area of classification for infinite dimensional or high dimensional data, is this paper that he wrote with B.S. Varadarajan, who is a very, very famous probabilist, and he was a PhD student at that time in the 60s. And C.R. Rao wrote this famous paper with him. It's for discrimination of Gaussian processes. And the word infinite dimensional doesn't appear anywhere here. As a result, if you do Google search with infinite dimensional classification, you will never find this paper. Okay? So a lot of people carry out research reinventing many of the results that are actually special cases of the results put by C.R. Rao and Varadarajan in the 60s. Okay. C.R. Rao and Varadarajan took a very fundamental result in this paper, and many results that we see these days, many theoretical results that we see these days on high dimensional, low sample size data, they are actually very special cases of Rao-Varadarajan. So Rao and Varadarajan considered the discrimination problem of Gaussian measures in Hilbert spaces. So they considered for Gaussian measures in Hilbert spaces, so they used the term Gaussian processes. They didn't use the term infinite dimensional space anywhere in the keywords or in the title of the video. Okay. And they realized, which was realized by probabilists before them, that for any two probability measures, whether they are in infinite dimensional spaces or in finite dimensional spaces, you can define a very general distance measure, which is called the Hellinger distance. Okay, and that can be defined for any two probability. It's a classic work due to Hellinger, and this distance is very fundamental in classification literature. And what happens is that when you have Gaussian distributions in finite dimensional spaces, this Hellinger distance and Mahalanobis distance are one function of each other. So all the results that you have seen earlier, they can all be translated or restated in terms of Hellinger distance, because Hellinger distance is just a one function of Mahalanobis distance in finite dimensions. Since we are almost towards the end, let me give you briefly what is there in Rao-Varadarajan paper. So this is a crash course on Rao-Varadarajan. Okay, so I think Rao-Varadarajan paper and subsequently the work of Kalladpur and others on a similar problem, which are on probability measures in infinite dimensional spaces, one can probably give a 1 year course. So what I'm giving you, a crash course on Rao-Varadarajan paper. Okay. So number one, if you have two Gaussian probabilities with positive definite covariances in finite dimensional spaces, they are always mutually absolutely continuous. That means one is absolutely continuous with respect to other. So it's like we can define likelihood ratio, and that's how we get the base classifier and the class boundaries. In infinite dimensional spaces, however, that is not true. Two Gaussian probabilities with positive definite covariance operators may be completely orthogonal. That means they might be sitting on two different parts of the space, or they may be mutually absolute. Both can happen. This is a beautiful result. This is the fundamental result in Rao-Varadarajan paper. And then the rest of the paper essentially works out very general conditions under which you have orthogonality and under which you have mutual absolute continuity. Now, orthogonality implies perfect separation between two. In a sense, now I am using the term that I have used earlier. The classification problem becomes degenerate and trivial. So there's perfect separation. So with enough amount of data, you can classify perfectly. It's like you'll be able to tell perfectly whether it's going to rain today if you have enough measurements on meteorology, enough meteorological measurements. You'll be able to tell perfectly whether it is going to rain or not going to rain. So, in some sense, the classification problem is trivial, and there is no point. So, there is no point in talking about likelihood ratio, base classifier in such cases, because the two probability measures are orthogonal. So, the real interesting case is when are they going to be mutually absolute? Here comes the next most fundamental result in Rao-Varadarajan. Two Gaussian probabilities with a common positive definite covariance operator are mutually continuous if and only the difference between their means. Now, these are infinite dimensional objects in an Hilbert space. They lie in the range space of the square root of the covariance. Now, this is the interesting thing that happens in infinite dimension. When we talk about matrices, when we talk about square matrices, if it is invertible, it is both 1, 1 and onto. The linear transformation it represents is both 1, 1 and onto. But that is not true in infinite dimensional space. We can have a positive definite covariance operator that is 1, 1 for sure because it is positive definite, but it's not onto. So its range space is not full. As a result, we might miss certain things in the range space. But if we don't miss the difference of the two means of the population from the range space, then they are mutually absolute. And once it is there, we can talk about this because it is in the range space. So we can talk about the inverse of the square root. And if you take the norm and square it, we get nothing but the Mahalanobis. So Mahalanobis distance will be well defined. And then the classification problem becomes a non-degenerate and non-trivial problem, and the likelihood ratio will become. So these are the two fundamental results in Rao-Varadarajan. Now, all the results that I will now see in machine learning literature, on statistics literature, on perfect separation for high dimensional data or non-perfect separation in high dimensional data, what are the class boundaries in infinite dimensional spaces, are derivable from these two fundamental results in some way. So I think that is what I have planned, and I think I have moved a little fast because I wanted to give you a complete history of development of classification by starting from Fisher and Mahalanobis and going up to Rao. A part of it is now forgotten by the machine learning and pattern recognition and computer science people, and so many of these things get reinvented. But this is an overall history, and this, in some sense, gives the fundamental theoretical basis for what we do for classification in finite dimension or infinite dimensions. This is the basic theoretical foundation that I have found. Thank you very much for your attention.
Thank you, Professor Chaudhary. It was a really nice presentation about the theoretical aspects about Mahalanobis and related stuff. I think now is the time for the participants to ask your questions, if any. Now we open the floor for Q&A. So you can also type the questions in the chat window, or if you prefer, you can also. Yeah, you can also.
I can stop sharing the screen for me, right?
Yeah, you can also unmute yourself and ask those questions if you prefer.
Yeah, Professor Chaudhary, I do have one question related to classification. We normally say some of an application. There are, in my application, I have used many classification algorithms, including the age-old problem, like there is a classification like nearest neighbor problem also. So how it is different from nearest neighbor and this almost because when I see the concept wise, it's almost like a similar concept. But how do I?
The Mahalanobis distance-based classification is really something like a nearest neighbor type classifier. You know, it's closely related. Okay. So when you calculate the distance, you can calculate the distance based on Mahalanobis distance. But the nearest neighbor classifier or the linear classifier that you get based on Mahalanobis distance or Fisher's linear discriminant function, they're not the same classifier. Okay, the nearest neighbor classifier will have different class boundaries. Okay, so they're not same, but I mean there are a lot of similarities.
Sure. Thanks.
So in nearest neighbor classifier, what you are doing is that you calculate the k nearest neighbors of the point that you want to classify, and out of this k nearest neighbors, you try to find out from which class you are getting most of the neighbors, and you classify there. Okay, so it's a way to see what is happening in the neighborhood, which points are in the neighborhood. So you see that basic idea is same. When I do this depth-based classifier, it is also doing something similar.
Thank you.
Yeah, I think Snehanshu mentioned about Euclidean.
No, I had just a comment, Vishwas. So, Professor Chaudhary, so when we have a depth-based classifier, so would you say that nearest neighbor is something like a depth-based classifier with a majority voting? The majority voting.
Can you relate it to some depth function? Possibly.
Yeah.
Okay, I think the real experts here are. I'll tell you without answering that. Before answering that question, I will tell you a joke, which is a standard conference joke. Okay, so there was a professor who was going around and giving talks in different conferences, and maybe many of you have heard this joke, but I like to tell you that. So it's like the professor was giving the same talk at every place, and the professor didn't know how to drive, so he was being driven by his driver. So the driver was also attending the talk. So after a while, the driver could memorize the entire talk and said to the professor, "You know, professor, I can give that talk also." So professor invited him and told him, "Okay, let's change our dresses, and then next time you'll be giving the talk." So the driver gave the talk, and he gave an excellent talk. But after the talk, there was a question, and the driver did not know how to answer the question. But the driver was very smart. The driver said, "Well, that's an easy question. I will let my driver, who is sitting in the audience, answer that question." Okay. So I requested two of my PhD students to come here. So I think Anil and Shubhajit, they will be the best person to answer this question. Is K nearest neighbor can be related to a depth-based classifier? Are they connected to the depth-based classifier? Shubhajit and Anil, are you there?
Yeah, I'm here.
Okay,
Can you
Anil,
hear
so
me?
what do you think? Yeah, we can hear you.
Okay. I don't know any connection between neighbor and best classification. So, but the nearest neighbor and Mahalanobis distance, they have different philosophy. In the case of nearest neighbor classification, what you are doing, you are computing the distance of a point, an observation that you need to classify. You are computing its distance from each and every point coming from that particular class. Whereas in the case of Mahalanobis distance, computing the distance of the point from the center of the data cloud, which is the mean. So in the case of Mahalanobis distance, you are computing the distance of a point from the mean of the two population, and then you are judging whether to classify this observation to this population or this population.
So I see now. So it is not really, you cannot really do it like a depth-based classifier.
And depth-based classification, yeah, in that sense, nearest neighbor classifier is different from depth-based classification. So I can give you one example. Suppose I'm dealing with a two-class problem, where one population is standard normal, the other one has the same. The other one is also located, but it has higher dispersion. Say one has the dispersion parameter identity, whereas the other one has a constant time identity. The constant can be bigger than or smaller than 1. Suppose that the constant is bigger than 1. In that case, what you hope that take any point on space, the depth of that point with respect to the population having higher spread will be bigger compared to the depth of that point with respect to the population having smaller spread.
So you
So
mean
if
that is
we
to,
go
that
for
is,
maximum depth class,
so Anil, you mean that that will be for most of the standard depths, you mean, right?
sorry?
So that the depth will be higher if you calculate some of the standard depth functions, right?
For the standard depth function.
Okay.
Because all our functions are Mahalanobis distance.
Yes.
And if you look at the Mahalanobis distance, one has higher distance than the other. So you'll eventually classify all observation to the same class.
Yeah.
But that will not happen for nearest neighbor classification.
Yeah, that's
you have
right.
very high demand.
But if your depth function is not a function of the Mahalanobis distance, then we don't do it. But if it is a function of the Mahalanobis distance, what you are saying is correct. That's right.
Yeah.
Okay, so anybody have any other curiosity?
Yeah,
I will try to answer it, or I'll request my drivers to answer it.
Yeah, I think there's a question from Saurav Chakraborty. What he says is, I think the sample version of.
Okay, I can see it on my chat box. Okay.
Okay.
Is it again? I think the sample version of Mahalanobis distance is defined by replacing the population mean by sample and population covariance. You are absolutely right. That's how it is done. If sample covariance is singular, then can we use G inverse or sample? Well, I mean, see, you can use some kind of an inverse, and you have to use some kind of an inverse. Okay, whether it is G inverse or some other regularized version, that depends on the problem. Okay, now, so this is the problem that you face when you have high dimensional data. Okay, so you have to do some kind of a regularization. One classic paper in this area is by J.D. Friedman that appeared in JASA some time ago. I forgot the year, but you can do a search. It's called regularized discriminant. So what J.D. Friedman essentially did is that J.D. Friedman put some special structure on the covariance matrix. Because you have a lot of data, you need to assume something. You need to assume some structure. So some of the structure that he assumed is, he assumed that there are a lot of symmetry in the correlations. So it's like all the correlations are same, all the variances are same, some such structure. Okay, that's a form of regularization. Or you can do some standard regularization where you add a constant times identity matrix and do the shrinkage type of operation. Okay. So some such thing has to be done, and then it will involve some tuning parameters which you determine by some cross validation method or something.
Okay.
Hello, sir. Yeah, Shubhashish here.
Okay, sure.
Sir, is there any connection between Hellinger distance and the support vector classification? The
I
problem.
don't think so, because support vector. See, that's like the
Mhm.
next generation. Okay, I think
Yeah.
after Rao, Fisher, Mahalanobis, Varadarajan, what
Yeah.
came really as a classic, in my opinion, is the Vapnik's learning theory, which came from the Russian school, and
Very
that led to
different.
this, it's a very different.
Very
thing, okay?
different paradigm
Yeah,
shift.
It's
Yeah.
a very different paradigm shift. What they are
Okay.
doing there is, it's like they are doing, it's like they are trying to locate the optimal classifying surface. Okay?
Yeah. Yeah.
And, they are trying to find that optimal classifying surface by optimizing certain criteria. And then they are trying to relate that to the misclassification rate, which is one of the
Yes.
most beautiful results in Vapnik's. Okay. So that's a
Yeah.
paradigm shift. I don't think,
Yeah.
well, of course, if there are elliptic distributions, then the best classifier will be what you get from Mahalanobis distance or Fisher's linear discriminant function, and the support vector machine will also converge to the same thing. Okay?
Equivalent. Okay. Yeah.
They'll be equivalent in some special situation, but that's the paradigm shift.
That's the paradigm shift. Okay.
Okay.
Yeah. Thanks
So
a lot.
that's the second
Yeah.
classic after the Rao Varadarajan work.
Okay.
The support,
Okay.
support vector machine and Vapnik's learning theory.
Vapnik's learning. Okay. Okay. Yeah. Got it. Thank you so much.
I think there is a comment from
There is a comment from Shubhajit.
Vijay. Yeah.
So Shubhajit said, yeah, there are some concepts of local depth, which is like a density estimate kind of thing that they have developed. Okay, so Shubhajit claims that that is weakly related to the, yeah, if you get your hands eventually out of your depth to density estimates, then it will be somewhat related to the nearest neighbor, because the nearest neighbor classifiers are kind of related to the density estimation with classifiers. So there may be some correction, quick correction there.
Okay. Yeah. Thank you, Professor Chaudhary. And over to you, Ramakrishna.
Will you able to see the slides?
Not yet.
Will you able to see the slides?
Yeah, you
Yes,
can
Yes,
see.
I'm able to see. Yeah, I can see it. I can see it. Yeah. It says loading something.
Yeah. Thank you very much for delivering such a